Hi, my name is Kaan Tasbas, and our project is Eyes of Argus. A quick introduction to begin. Computer vision is the science and technology of how computers can be made to gain high-level information from images or videos. In short, it's an automation of the human visual system. Stereoscopic vision, to build on that, is the extraction of 3D information from digital images. And this is extremely similar to how human depth perception works with our two eyes. The problem with stereo vision is the inaccuracies in the system if you select an incorrect baseline for the application. And the baseline is the distance between the cameras, and we're going to see a little bit later how this affects the actual calculations and the quality of the image. So we hope to make a more robust and accurate system that utilizes multiple baselines. A couple of use cases for stereoscopic vision include automotive and robotics industries. The World Health Organization reports over 1.25 million deaths per year due to traffic incidents, and that's on track to become the 7th leading cause of death in just a little over 10 years. And this is important because autonomous cars are now almost a household idea, and it's thrown around a lot in the media. So everyone knows about autonomous cars, and stereoscopic vision definitely has a very large use case within that field. Within robotics as well, stereoscopic vision can be used in research specifically to analyze environments, to take three-dimensional pictures of environments, and in the commercial industry, it can be used on delivery robots, such as those being developed by Amazon and FedEx, and in warehouse operations, where robots will move around boxes and control the overall operations of a warehouse. A couple of alternatives include LiDARs, which use lasers to measure distances, and radars, which use high-frequency electromagnetic waves to measure distances rather than the images used in a stereoscopic system. However, a couple of issues exist with both of these. LiDARs are susceptible to particles in the air, such as rain or snow, so if you have inclement weather, you won't be able to use LiDARs to analyze much. And they also have a blind spot in the short range, so you can see in the image to the right that the very close ranges around the LiDAR you cannot analyze. And in radars, there's a phenomenon known as multipath, which causes erroneous readings. If the signal bounces off of a secondary object and returns, it's impossible to calculate the true distance to the target object. This is a picture of our platform with the cameras mounted up top. You can see the cameras are on a rail, and so that's how they move back and forth. In a video we'll see a little bit later. And in the middle, below them, is the computational power, so the Intel NUC, along with the power system. Traditional stereoscopic vision includes two cameras that are placed on a plane, and the images retrieved from these two cameras are then analyzed, and similar objects are matched along both images, and then information from here is used to calculate the distance to an object. These pictures show the difference between the left and right images. On top we have the left, on the bottom we have the right, and you can see that the objects don't line up perfectly, and this difference between the image is actually how we calculate the distance to an object. Now we use this difference to calculate what's known as a disparity, and that's simply the left minus the right, and that's just a pixel location. So you can see in the coordinates that we take the x minus the x of the left minus the x of the right, and we get a number 117, and that's a disparity that then correlates to the depth of the object. This picture is to help explain the baseline, which is the distance between the two cameras. You can see as the baseline increases, the overlapping area between the cameras decreases, and this results in a farther minimum distance that the camera objects can see. And as the baseline gets shorter, the minimum distance you can see is also shorter. However, it can't see as far away due to the information in the image. These are three disparity images that we retrieved from the short, middle, and long baselines. The top left is the short, top right is the middle, and the bottom right is the long baseline. And the object is at 0.5 meters. The object in this case, a human body. And you can see that the short baseline is able to pick up the object and display it in the disparity map. However, the medium and long baselines cannot pick it up, and this is due to the longer minimum distance that the two of these have. These are the disparity images of the short, middle, and long again at a 2-meter object, and you can see this time the short baseline cannot pick up the object because it's farther away, and then the middle baseline is able to see it much more clearly. The long baseline has some of the object, but not nearly as much resolution as the middle baseline. And here is an object at 4 meters. The short and middle baselines have almost no information about the object itself, but the long baseline is able to pick up the majority of the object. The purple in the middle you can see as the body. This is a quick demonstration of the camera system actually moving. On the left, you're going to see the real-time images from the cameras, and below that is the disparity image being calculated. You can see that the cameras stop momentarily at each baseline to capture an image and continue along their pattern. Depth is a relatively simple calculation. It's the focal length of the system multiplied by the baseline and divided by the disparity, and this is why we focused on disparity so heavily, because the depth is inversely proportional to this disparity. The baselines we used in the project were 9 centimeters, 24 centimeters, and 39 centimeters. A couple of future goals we hope to meet include combining the 3 disparity images of the short, middle, and long baselines into a single disparity image, and we also hope to characterize the baseline error that's due to the stepper movement in more detail so we can take it into account.